Okay, this is my third and probably final video for now on using the SkySieve software. Um, Using the same design that I had before. It's not complete, but for the purpose of this, that will be fine. And I'm going to focus in this video on um, applying the loads and making sure the supports are correct, and then looking at the analysis that you get from that. So as you can see, I have made a slight modification to my previous design. I've already got the materials and sections assigned. I've got my spaghetti there with the correct sizing. I have made my dimensions slightly different for this bridge that I've been working on, and I did all that just by going into the Node spreadsheet. I actually used Excel to calculate this for me. I made this, relatively speaking, half the width of what it was, but I've also changed the sizes of all of these down so the bridge now spans a total of 40 centimeters, which is closer to the specification of what we're going for. And you could see in the 3D render that it actually looked more reasonable as well with the spaghetti dimensions the way they are. So anyway, let's move on. What I'm going to do is I'm going to start by adding my supports. So we're going to add supports that any typical well-designed truss bridge would have. Using the completely fixed support at both ends is not going to be very accurate to what we will be doing, because we're just putting our spaghetti bridges across two desks or across a loading system platform. The points of contact are not actually fixed in any way. We're not gluing them down to the desk. So the bridge is able to flex and move relative to the desk a little bit. Any typically well-designed bridge will actually have a pin support at one end and a roller support at the other end, and that allows it to flex appropriately, but it does fix it at one location so that it can't actually slide on the x-axis. Essentially what we'll be doing is sort of like two roller supports, but that's not allowed in good bridge designing. So we're just going to do the pin support at one end and the roller support at the other end, which is what you would normally do. So we're going to have 4 supports in total. 1, 2, 3, and 4. Let's start with one new. Our first node ID will be node 1. So we're going to apply a pin support at node 1. We hit apply, and there it is, and you can see the code there matches what you get when you select the pin support. We want another pin support at node 10, which is node 1's partner there, the equivalent, so node 10, and we'll apply that. And then up the other end at node 5 and 14, we actually want our pin with rolling support. Okay, so node 5, pin rolling support, hit apply, and node 14, pin and rolling support, and hit apply. Okay, so that's all the supports we should need. Our bridge is supported appropriately at both ends. If we had lots and lots of overlap, we might even add supports in this point here, but typically that's what you're going to have. So that's pretty easy. Now in terms of adding our loads, we can either do point loads or distributed loads. Ultimately what we'll be doing is simulated best by a point load, because we'll have a loading plate right in the middle of the bridge. Now when you test your actual bridge and according to the competition rules, the loading plate will actually sit right here somewhere in the middle. There's no specification of how wide your bridge needs to be, so you can make it essentially the width of the loading plate if you want to, and that will probably be the strongest sort of bridge that you can get. It doesn't need to be a sort of specific bridge in terms of being able to carry width of traffic or anything like that. There's no specific rules on those dimensions. So you can make it whatever width you want it to be, but there will be a point load essentially right in the middle. So let's have a look at our point loads and see what we can do with them. Very simple. We can either add it to a node, or we can put it in some point along a member. So let's do a node one first. I'll do a couple just to show you the different things that we can do. So I might want to put a point load at node, let's say 12 in the middle here. I don't have any cross support, so I'm not going to worry about that. But I'll put a point support at node 12. The x magnitude, which is this direction, is going to be 0 because my point load is going to go directly down. So my y magnitude is negative because it's going down, and you can see according to this, positive is up, so negative must be down. And this is measured in kilonewtons. Now 1,000 newtons is approximately 100 kilograms. Works out that 1 kilogram is 10 newtons. So in terms of what we're aiming for, if you can hold 100 kilograms or more, that is brilliant, and you'll be in real good competition. But to be fair, we just want to do a reasonable load. So 1 kilonewton, remember, is 100 kilograms. So I'm going to start with 0.5 kilonewtons. I think that's fair enough. That's actually 50 kilograms. Z magnitude can be 0 as well because we're not applying any load in this direction here. And you shouldn't have to worry about that. If I hit apply, I can see my 0.5 kilonewtons acting directly down at node 12 there. Alright, if you don't have a node in the middle of your bridge and you've actually got a member there, you may want to apply a point load along a member. And so I might do this at member 32, just because that is a member that I have in. So if I go 32, I can choose the position along the member. If I want it directly in the middle, I might do it at 50%, which would be right in the middle. And all of the rest is very similar. 0 in the x direction. My y magnitude will be negative, let's go with 0.5 again. And my z magnitude will be 0. And I hit apply, and that has put a load in the middle of my member. So those are probably the only two things that you're going to be dealing with. There is an option to do a distributed load, but this is more designed for a load that's going to be distributed along a whole member, and you can actually have a different starting magnitude and it can be varied along it, and it's a lot more complicated than what we really need to do, but feel free to have a play with it if you want to. Once I have my supports and my loads all assigned correctly, and I've done my materials and my sections, I can now solve this truss. So there's been a recent change to the program, in fact, in terms of up here. There's a new feature called design, which you can have a play with, but I'm not going to play with in this video. We're just going to do a standard solve, default, and it might take a little bit of time to calculate. It won't take very long for me because this is a pretty simple bridge structure, and this is what I get. So I can go through here, I can look at the reactions, which shows what's happening at my supports there. Now, because my truss structure is rather incomplete, it's not what you'd call statically determinate at all. There's a lot of sideways forces, and because I applied my loads in different positions here, this is not a very stable bridge at all. We can have a look at my axial forces as well, which shows all the internal forces. So there's a fair bit of compression happening there, as well as tension. And you can see the red is compression, it's got a C in brackets to remind you there, and the blue is in tension. And it is sort of operating like any standard truss bridge would. The bottom members are all in tension, the top members are in compression, but it's not too good that these members are under as much strain as they are, I suppose. Although it's probably not as bad as it could have been, considering it's a very incomplete truss and it's very basic. Displacement might be a handy one to look at, and that actually shows with the black writing sort of how that bridge is moving. And you can see that because I don't have any cross members, bracing members along the bottom, my bridge is actually buckling straight out there. So you can sort of see that. However, in this view, you can see that it's quite busy. There's lots of numbers and busyness all over it. The colors isn't too bad, but it's not the best view for looking at displacement. So I'm going to go to the 3D renderer, and you do this after it's been solved. And if you do it after it's been solved, you'll get these options down the side here. It's a lot less busy than the other menu. Basically, we have deflection, and wow, my bridge is getting completely destroyed. So this is true deflection scale. Okay, so you can actually do a number of different scales. There's none, true, which is what actually is happening to your bridge. My other bridge doesn't deflect as badly as that, but this one's getting quite the workover. And then if the true scale is not truly expressing what's going on, you can actually slide it up and see that exaggerated in different sections there. So we've got automatic, which will sort of give you a better representation of what it's doing. So you can actually see your bridge flexing. You can also hit member results. And in here, the two things you'll probably be most interested in is the axial force, which we looked at before, which just uses a nice color coordination. It doesn't overcomplicate the image with messy numbers all over it. Basically, the blue is in tension just as before. The red is in compression. And if you're interested in how much, there's a scale up here that sort of tells you how much force is on those members. And then you can also look at displacement sum, and that will, in a similar sort of scale, blue being not moving at all. Okay, so those top ones where I put those cross braces aren't really moving, but as we saw, this part here is going to flex out quite a lot because there's no cross members, and we can see that that is deflecting by 912 millimeters, which is quite a lot, which is why when I had my deflection scale on true, it was very exaggerated because that's deflecting by almost a meter in the outwards direction there, and you can see what's going on. So my bridge is completely destroyed. That is what spaghetti looks like when it's cooked, but hopefully these features will help you in analyzing and doing a quick comparison of different truss bridges and then designing your own bridge. All right, thanks very much. All done.